Hello, guys. Welcome back to MedZone African Motives. We are still on our industrial electronics N3. Previously, remember, we did or worked with the DC theory from our industrial electronics N2. So there are some other basics that you actually understand from the direct current theory. So working with the DC current, it is something that is important in your syllabus. Just considering a normal resistive circuit that we are given, whereby there is a certain voltage across this resistive circuit that you are given, a current flowing. What is it that we do understand about this DC circuit? The current being equal to the voltage over the resistance. We can also calculate the power that is across this resistive circuit. It's an element that you're talking about, this resistive, where power can be calculated from I squared times R. There are so many ways that you can use to calculate your power from your formula sheet. There are so many formulas that you are given that you can work with. Power, which is equal to the voltage times the current. Power, which is equal to V squared over R, measured in watts. These are some of the other things that you can have. From this formula, you can even, V is equal to current times the resistance. So in a normal simplification, we are not going to have that basic question where you're just given a resistive circuit like that. No. In our N3, we are going to focus with what we refer to as the Kirchhoff's law. The Kirchhoff's laws, they want you to understand the Kirchhoff's laws in your syllabus. All right, so what is it that we are referring to, or that we are talking about the Kirchhoff's laws in a DC circuit, or considering a normal consideration of a circuit? All right, like we are saying, there are laws, meaning to say we're talking about more than one, okay? So there are actually two laws that we are going to talk about, which is the Kirchhoff's laws. So the first law, it states that if you are given, that is the first law, which is the current law. So the first law is referred to as the current law, okay? So it is stated that considering a junction, which is at a certain point, the currents are flowing to a certain junction. Okay, there's a current flowing towards a certain junction. There's a current flowing towards the junction. Then there's a current flowing away of the junction. Another current is flowing towards the junction like this. These are currents which are flowing towards a certain junction and another current flowing away. Let's say this is current 1, this is current 2, this is current 3, and this is current 4. When the currents are flowing towards the junction, all right, so the arrow here is indicating that it is flowing to the junction, the arrow. Okay, if it is like this, it is flowing away from the junction. This one is flowing to the junction. So it is stated that these currents, they have got a relationship. The relationship is that the sum of these currents, the sum of these currents must be equal to 0. Everything that you are having here must be equal to 0. So if something is flowing towards, you're going to take it as a positive. So that means we are going to have current 1 plus current 2 plus current 3. These currents, they are flowing towards the junction. They are going to be positive. Current 4 is flowing away. It is going to carry a negative. So if we subtract this, the sum of everything must be equal to 0. the algebraic sum of the currents entering and leaving a junction is equal to 0. The algebraic sum is equal to 0. So with this, we can conclude that, let's separate this now. We can conclude that the currents that are flowing towards the junction, the sum must be equal to the sum of currents leaving the junction. So we can conclude to say the sum of currents entering or the junction. So you can just say entering the junction is supposed to be equal to the sum of currents that is leaving the junction. So these currents are supposed to be leaving the junction, which is our junction is the point that is this part. That is the junction. So in actual sense, we can even express it mathematically. Remember the summation. So you can say sum of currents entering the junction is equal to the sum of currents leaving the junction, where this is the sum of the summation, the sum. So according to this example that we are having, according to the diagram, these currents, current 1, current 2, current 3, they are entering, they are pointing towards the junction. So you can conclude that current 1 plus current 2 plus current 3 is equal to current 4, which is leaving the junction. That is what you can present. This presentation and this presentation is the same. So we can use this to even calculate anything that we want. So it is from the type of the circuit. With this current law, take note, it's a circuit that you're given. Maybe the current is entering, then you're given something of this nature. All right, this is the current. You're talking about current 1, and maybe this is current 2, and maybe this is your current 3. This is the junction according to the circuit. They meet at this point. So current 1 is entering. Current 2 is leaving. Current 3 is leaving according to the arrow that you are given there. It is going away. So it means the current entering, which is current 1, is supposed to be equal to the sum of these ones which are leaving the junction, which is current 2 plus current 3. So it is all about how the diagram is presented. How is the diagram presented? So that is the Kirchhoff's current law, stating that if you're dealing with the currents, you can add the currents entering and equate to the currents that are leaving the junction. All right, that is the first law. Then the second law is on the voltage. That is the second law. So the second law is considering as the voltage is considered as the voltage law. So what is it that you're considering about the voltage? Considering a closed loop where we are given resistors in a closed loop, right? This is we've got a certain voltage, and this is a closed loop where you're given resistor 1, resistor 2, and there's a current that is flowing and having a total voltage or the total EMF of the circuit. It states that the sum, if you want to consider that part, the sum in a closed loop of the voltage drops. Sum of this voltage drop, each and every voltage drop that you're going to have, the voltage drop on this part is equal to the potential difference that you are given. Remember, across this resistor, there is a voltage V1. Across this resistor, a voltage V2. So according to the current, because this is according to the current, once there's a current and resistance, a voltage is generated. There's a voltage. So you're generating a certain EMF from there. So if you're to consider in terms of the voltage, the total, it was supposed to be V1 plus V2. According to the number of voltage drops that you are considering. But let's talk in terms of the current times resistance. That is what is giving us voltage. Current times resistance. Current times resistance. Remember, in a series, current is the same. Remember, in a series, current is the same. So meaning to say the current across R1, the current across R2 is this total current that we are given. So the voltage drops, these are the ones that we are considering. The algebraic sum of the potential differences. So this is the sum of potential differences. All right. So with the algebraic sum of the potential differences, which is the voltage drops that you are given, it must be equal to the one that is the voltage drop. So we are saying the algebraic sum of all the EMF and the voltage drop. So in a closed loop, therefore, we can conclude that the algebraic sum of EMFs, which is ET, the algebraic sum of the EMF, they can be given EMFs that are there. You have to combine those EMFs. So this is the sum of the EMFs. So you can just say sum of EMFs must be equal to the sum, which is the algebraic sum of the potential differences. So these two laws can be used hand in hand. The current law and the voltage law. We don't just expect a question. Yes, we can have a question which is just on the current law. But do not just expect to have something like that. We can have questions now covering both voltage and the current law. So we want to see always the direction. So some of this part of the currents, the flow of the currents, and the potential differences, how to calculate the potential differences, this and that. It's you have a basic from your circuits, electrical circuits from N2. But let's consider typical examples. Let us just say we are given, I'm just going to consider this example here. Let's say we are given, so here I'm just going to have a sketch. Yes, just a sketch, guys. Do not mind my diagram. I just want you to understand how questions might be given. Let's say you're given a typical circuit of this nature where it is a series and also a parallel. Remember, the idea of the parallels, we are not considering those like calculations of parallel like what we had in our N2A. You have to calculate the total of the parallel, the total of the no. We are not considering like our engineering science where you'll be asked to calculate the total resistance, the total current, this and that. No, we are focusing with the Kirchhoff's law. That is the major part of your syllabus. Okay, so let's say you're given a circuit of this nature, and this is the total current. Let's just say this is I1, and this is A, B, C, D, and we've got E here. Let's say E and F, and we've got G, H. So in most cases, you'll be given a certain consideration, just like the example that I'm giving you here. That is how exactly even your typical exam questions might be given as. So what you just need is to understand how these questions are given. That is, like, how are they given and how do you attempt the typical questions? So in terms of the currents, they can name these currents for you. Current 1, then they can name current 2 for you. Then they can even name this current, but I'm not going to name this current. I'm just going to leave it like this so that we apply together how are we supposed to obtain that current. Let's say the question is to determine or to find using the Kirchhoff's laws. Remember, we are using the Kirchhoff's laws. You want to determine the value of current 1 and current 2. Determine current 1 and current 2 using the Kirchhoff's laws. All right. So the question is, how are we going to apply or use our Kirchhoff's laws to determine these two currents? The first thing is to formulate the currents entering, leaving the branches. So in terms of current 1, this is the current entering. Okay, sorry for that. I want you to see this. The current 1 is entering. If you have to consider this, it is entering the branch, entering this loop that you're given, which is the junction at this junction here. At this junction, let me just increase so that you understand what I'm trying to say here. At this junction, current 1 is flowing. This is your current 1. Remember how the current flows from the positive side. All right. So the current is flowing. This is I1 flowing, flowing. It enters at this point. As it enters, another current is branching this side. Another current is branching this side. That is how the current is flowing. So the current entering, which is this I1, it is entering. It is giving us these two currents. But one of these currents, let's say this is I2, this one. Let's say this is our I2. What will be this current? I don't want to write this as I3. I don't want to have 3 unknown values. I want to write this current here in terms of I1 and I2. Okay, for now, let's say I do not know this. Let me just say it's IX. We're supposed to name I1, I2, I3, which is fine. But we want to avoid like having 3 unknown values because we are going to solve simultaneous equation at the end. And if you're given 3, it's going to be difficult for you guys in your syllabus. Just avoid that. This is your, for your N4, that is where you deal with those 3 unknown values. But for N3, just focus with 2. So how are you going to formulate the equation? This is what you're going to do. You're going back to this IX that you are having here and formulate an equation using the Kirchhoff's current law because you are referring to the current. Remember, we said the sum of current, we can just say the sum of current in, that is entering, is equal to the sum of current out, which is the sum of current leaving the junction. I1 is entering the junction. So that means I1 is equal to the sum of these two, which is I2, and the unknown current that we want to find in terms of I2. And so we add I2 and I1. So IX is the unknown current that we want to determine in terms of I2 and I1. Since we do not want to have a lot of unknown currents, I1, I2, I3. So we transpose I2 to the other side, it becomes a minus. That's I1 minus I2 is equal to IX. Remember, this is an equal sign that you're having here. So IX is equal to I1 minus I2. So in place of this IX, instead of me writing this as IX, I'm going to write it as I1 minus I2 in terms of what I'm given already, I1 and I2. So this is going to be current 1 minus current 2. It is not just something that is or formulated, just given, no. It is formulated. We formulate it from the Kirchhoff's current law, the current, because sometimes they're not going to give you a complete diagram with currents like this. If you are given a complete diagram like that, it's an advantage if it is like that. But do not expect that you are going to be given a complete diagram like that. No, don't expect that. So now with this, we have named our currents. We have current 1 entering, current 2, current 3, which is I1 minus I2. So remember from your voltage law now, because we want to find this unknown. The voltage law, it also has the currents are involved in this voltage law. So what you are going to do is to create equations from the loop. You are going to find a loop of your choice. You create equations. You create equations from any closed loop, as long it's a closed loop. Okay, this is what I'm trying to say. Let's say we want to consider this loop. This one, it's a closed loop moving here. It's a closed loop, this one. It's a closed loop, it's closed. It's a loop. So you can consider how this loop, how the voltages are taken, because we said in a closed loop, this is our voltage law. In a closed, it must be in a closed loop. EMF, which is the sum, must be equal to the sum of the potential differences. So what we need is to have the potential differences. So this is what we are going to have. The sum, that is the ET, the sum of the, so we can just say ET just in short, just gonna write in short, ET, sum of ET, which is the sum of the EMF that we are given, is equal to the sum of the current times what? Current times resistance, which is the voltage drops, the PDs along each. So I'm going to consider the loop, the first loop. Let's say I'm starting from this A, like this loop here, A, B, C. This point is not given, so I'm just gonna consider G. So it's A, B, G, F, then E, then I move to this side to H, okay, to the point H, then to the point A, back to the point A. Okay, so like I said, this way, like this, back to the point A. So this is how I'm going to take the loop. This is how I'm going to take my loop, or the direction. I'm going to take it this way, this way, this way, like this way. This is how we are going to move. Okay, how are we considering the direction from the positive side? Remember how the current flows, because there is a voltage there. There's a source of voltage. So you have to consider that positive. If you move this way, you take it as a negative. Okay, the moment you oppose the direction, you take it as a negative. So ET, which is the sum, ET is 10. So from this loop, okay, let's take our loop. We said it's gonna be A to B to this point G, from G to F, from F to E, from E to H, from H back to the point A. Okay, so if you consider from E, I want you to see what is happening from E, from the point E here. It is the same current flowing from E here. It is the same current, which is current I1, up to this point here. It is the same current flowing in this loop, in this from this point E up to. And what is that current? It's current I1. So meaning to say this 10 volts, because we are maintaining the way it is supposed to be from the positive, that is how I'll take our current. So it is going to be the voltage drop now. Which current is flowing across here? It is I1. Are we having a resistor from E back to this point here? Are we having a resistor? There is a resistor there of 5 ohms. So that is our voltage drop. 5 times I1 current, the resistance and the current together, which is current times resistance, to give us the voltage drop. So that is 5 I1. Remember your theorem, your law, the sum of the potential drops. So it's a potential drop that we are having there. We are maintaining the current is flowing. It's in the positive way. It's flowing. It's maintaining. The arrow is maintaining as it is. Then we move on. From this point of our diagram here, along this part, it's part of our, the way the current is also here. But this part here, there is a certain current that is in this branch. This branch where we have G, F, back to E here, in this branch here, on this part, there is a current flowing, which is I1 minus I2. So the question is it maintaining this direction of current that we are, is it maintaining? Yes, it is maintaining. So it becomes a positive. If let's say this current was taken like this, it was opposing, the arrow was like this, it was going to take a negative sign. But if it is maintaining the sign like this arrow here, it is maintaining how our current is moving, how we took this loop. The way that we took our loop, it is this way. And the current is also flowing in the same direction. So it's going to be a positive. Remember, current times resistance. There's a resistance there of 10 ohms. So it multiplies the current, which is current 1 minus current 2. The current that is flowing in that branch. That is how we take it. The current flowing in that branch. So we formulated an equation. You can just simplify this as simultaneous. So, I mean, they have two unknown values there. So just expand brackets from your mathematics. 10 times I1, that's 10 I1. 10 minus 10 I2, you can collect like terms. 5 plus 10, that is 15. So that is going to be 15 I1 minus 10 I2. So this is our equation 1. Okay, so a formulated equation 1. Guys, the way that you are going to formulate these equations, it's in your hands. As long you are taking a closed loop, does not affect anything. It does not, it's not even a problem. So a formed an equation, just leave because there are two unknown. We cannot solve this equation. We have to find another loop to work with this time. All right, so this time I want us to consider this loop here. All right, remember, I want to find I1 and I2. So just for the sake of seeing properly our diagram, I'm just going to consider another loop here. So this time, let's consider another loop. Which loop can we take? We can even take it from this one. This one is a closed loop from C to D, back to E, back to this point here, back to here. It's a closed loop. The way that we are taking from E this way, this way, this is the way that we are moving. This is the way that we are moving. We want to consider this loop. So this is loop C to D, to E, to F, to G, back to C. All right, so this is the loop that I'm going to take. According to the loop that I'm taking and the movement that I'm having, and in this loop, are we having a voltage source? Are we having the EMF there? We do not have. In this loop, it's a closed loop as we can. Yes, it's closed, but we do not have a voltage. But the idea does not change that the voltage drop is supposed to be equal to the sum of the voltage drop is supposed to be equal to the EMF. But even if we do not have, it means the EMF is 0. So you're going to take your EMF as 0. But the voltage drops, we can have the voltage drops. Let's consider from C to D across this, there's an 8 ohm and there's a current I2. This current I2, is it following the direction how we took the loop? Yes, it is following exactly. Take note, this is our loop. C, D, we took it this way. And the current is flowing in the same direction. So it means it's going to be a positive. So this voltage drop is a positive. 8 times what? 8 times current 2. Okay. Let's move on to another part of the circuit. From point E to F to G, this part here up to this point, if you consider there's a current that is affecting this branch here, the current flowing, it's I1 minus I2. I want you to see the direction of I1 minus I2. I1 minus I2 is moving this way. This is the direction of the arrow. It is going this way. But the way that we took the loop from C to D to E, we are moving this way. This is the direction of our loop. This is the direction that we took. These two, they are opposing each other. The current is moving this way. The way that we took the loop is this way, other way. They are opposing. So if they are opposing like that, it is going to be a negative. That means the voltage drop there, we take it as a negative, so it will be minus when it is opposing. So that means current times resistance. The resistance is 10. The current is what? I1 minus I2. But you take it as a negative because the way, the direction of the current and the direction that we took our loop is opposing. So it becomes a negative. Then you formulate your equation. So that's 8I2 minus 10I1 minus 10 times minus, that's a positive I2. So that means taking I1, that's minus 10I1, 8 plus 10, collecting like terms, that is 18I2. So we have formed an equation with I1 and I2, which is the second equation. So this is enough. Once you have got two equations, you have to solve for I1 and I2. So I do not know the way that you are going to take another loop, or you're going to consider the loop from this way, considering the outer way like this, as long it's a closed loop. Guys, the formulation is in your hands. At the end, these currents are going to be the same. Despite the way that you have taken, you have used this loop and that other loop, at the end, the values of the currents are supposed to be the same. So this is what you have. We have got two equations. Since you want to find I1 and I2, we are now just left with solving of these two equations. So you can just have our equations, since these are simultaneous from our mathematics N3. So we have to solve the equations. All right. So let's solve. Remember the equation 1, we can just start with the currents. That is 15 I1 minus 10 I2 is equal to 10. Then from equation 2, that is minus 10 I1 plus 18 I2 is equal to 0. So these are the two equations that you are going to solve. By solving these equations, you're determining current 1 and current 2. So how do we solve? It's either you're going to use substitution, you're going to use elimination. It's in your hands. So in most cases of your syllabus, you're going to see these guys using elimination method. How do you eliminate? From our mathematics, there are two equations that we are given here. So it's either you want to eliminate current 1 or you want to eliminate current 2. It's in your hands. It's in your hands again. So if you want to eliminate, let's say we want to eliminate current 1, you interchange these numbers. The 10 multiplies on top. This 10, it multiplies equation 1. 15 multiplies equation 2. Remember your elimination, you want to make these two to be the same so that you can eliminate. Yes, you can even use the sign minus 10, but you can even avoid the sign. Just work with the 10 as it is. Okay, so this means you are multiplying 10 times 15, which is going to be 150. I want 10 times minus 10, minus 100. I2, 10 times 10, which is 100. 15 times minus 10, minus 150. I1, 15 times 18, that's positive 270. I2 is equal to 15 times a 0, that's a 0. So you want to eliminate you want to get rid of I1. Already the part of I1, you can see that I1 is the same. You want to eliminate that, and you can see that I1 is the same. But here it's a positive, and this one is a negative. So how are you going to eliminate? Are you going to add 150 plus minus 150 to eliminate? To eliminate is to remove. Are you going to subtract 150 minus 150? So you have to choose the sign. Is it a plus or is it a minus? So if you subtract, it will be minus, which is a plus, which is 300. You have not eliminated because it will be 300 I1. But if you put a plus, it's plus and minus, that's a minus. 150 minus 150, that's a 0. That is, we have eliminated this current. So in order for us to eliminate this part, we are going to add the sign that you are going to choose is the sign that when you put that sign here, you are supposed to obtain a 0. So if you add 150 plus minus 150, that's a 0. You have eliminated I1. So this sign, you use it throughout. You're going to add again, minus 100 plus 270. Plus and the plus, guys, that's a plus. So this was going to give us 170 positive 170 I2 is equal to add again 100 plus a 0. You add, that's 100. So the sign that you are using here, you use it throughout. Okay? So you want to find I2, you can divide by 170 to find I2. That is, I2 is equal to 100 divided by 170. That's it. So that's you're going to obtain I2, which is 0.588 amps. Remember, you're talking about current in this case. That's I2. So to determine I1, it's again in your hands. Are you going to substitute this value or are you going to eliminate I2? It's up to you. You can even substitute. From these two equations, we have got current 1, we have got current 2. We can take any equation. So I'm just going to take in any equation. So from equation 1, that's from equation 1, we are given that 15 I1 minus 10 I2 is equal to 10. It's either you can take equation 2. It's up to you. You can take any equation that you want. So in this case, I take I1. I'm going to substitute this current. Where there is I2, I'm going to substitute I2. That means 15 I1 minus 10 times I2, which is the one that we calculated, 0.588, is equal to 10. So that's 15 I1 is equal to, remember, this is a negative. You can even multiply these two. You can take it on the other side. So it becomes a positive 10 times 0.588. You combine everything, you divide by 15, guys. This is in your hands. You can multiply, add to 10. Then whatever that you get, you divide by what? By 15. By doing this, you're obtaining the value of current I1, which is going to be something like 1.059 to 3 decimal places. So that's the idea there. Remember from your mathematics, we talked about how to round off to 3 decimal places on your calculator. So you can even set your calculator to that. So each and every part that you'll be given, it's not like you're going to work with a direct current, like you're just working with a normal circuit. No, it will be a combination. It will be a combination that you're working with, where the Kirchhoff's current law is to be applied, and also the voltage law is to be applied at the same time. So you're working with two things there. So in most cases, you'll be thinking, when it is Kirchhoff's law, I'm just working with current. No, it's not just about current. All right. Let's consider another example. So in this case, I'm just going to have examples. I think, guys, if you see, we have talked about most of this part, actually talked about this from our question papers. And these examples, guys, you see, engineering, if you check, you revise more question papers because even those examples that you have in your textbook, it's exactly the way that the question papers are actually asking. They just give you one or two things. Then from there, you see the example is just, it's an exam. It's an exam question. So do as many question papers as you can. That is how you can actually win in this engineering. So you can actually be given a bridge. We can have a bridge circuit like this. It's not like the first time, like for those who have been revising, I think with some question papers, we have seen typical questions where we worked with a bridge circuit. All right, so this is, guys, just a sketch. You can draw something that is, actually, you'll be given this diagram, so do not worry about this. Here is mine. So let's say you're given a circuit which is already complete. You are given 2 amps. This is current 1. So sometimes they will give you everything. Current 1. This is resistor 1, 2 ohms. And we have got R4, which is 9 ohms. Okay, R3. All right, so guys, I'm just gonna draw this diagram so that we are together. Okay, so let's say this is what we have, and this is 18 ohms, and you're given everything, the currents. You're also given this current, remember from the formulation that I talked about there, but they can even give you everything. This is 2 minus I1. This is I1 minus I2, where this is I2. So these arrows, they are not just given for just to be given to say it's an arrow. They have got a meaning, as we can see from what I was explaining. The direction, how the current is flowing is important. Let's say they were given 2 minus I2, and we are also given at the end 2 amps. And using the Kirchhoff's laws, you're asked to find or to determine I1 and I2. Just like the previous case that we had using the Kirchhoff's laws. And you'll be given points. This is A, this is B, this is C, and this is D. This is what you're given. It's given. This diagram they gave you. You're not formulating, and they gave you as it is like this. And the question is, determine I1 and I2. How can you determine I1 and I2? So again, you have to formulate everything, guys. It's about formulating. Which loop can you consider? All right. Let's say I consider this loop from A to B, back to D, back to A, like this. Let's say I consider this loop. All right. So this, from this loop, which is loop, because already the currents are there. There's current 1. We are not calculating. We are not like formulating the currents because they are already given. So it's just determining, finding. So this is A, B, D, back to the point A. So according to this loop, remember the concept, the sum of the voltage drop must be equal to the EMF that is given, which is the total EMF. Are we having any EMF in this closed loop? No. So that means we are taking it as a 0. So the sum of the voltage drops, let's consider how we are taking the loop. A, B, D to A. This is the way. So from A to B here, there's a current and a resistance. So you can have a voltage drop here. But the question is the current flowing in the same way that we took the loop? Yes, it is maintaining. This is the way our loop is taken. So it is maintaining. It's a positive voltage drop. So it's going to be 2I1. Okay. We move on from B to D. From B to D, the current is also maintaining. Look, the current is going down. This is the way our current, the loop is taken. So it's maintaining the direction of the arrow. So it becomes a positive as it is. So 6 into I1 minus I2. From D to A, if you check from D to A, the loop is, this is a loop, but look how the current is going. The current is going this way. The current is opposing. The loop is going this way, the current going that other way. So I said whenever it is opposing like this, it will be a minus. So that's minus 9 into the current. The current there is 2 minus I1. Just like that. Resistance is 9. The current is 2 minus I1. You're already given that. You're already given. You work with the diagram that you're already given. So you formulate according to the diagram. It is opposing the way that we took the loop. If it was maintaining, it is a positive. So it depends with how you took the loop. All right. So thus we have formulated an equation. So this will be 2I1, 6I1, 6 times minus, that's minus 6I2, minus 9 times 2, which is minus 18, minus times minus, that's positive 9I1. All right, so let's take the 18, the minus 18 to the other side of the equation. So it can be a positive, it was a negative. So 18 is equal to, collect the like terms, that is considering current 1. We also have current 1 here. We also have current 1 here. These are the like terms. So we're going to add these currents, all right? That's 2 plus 6 plus 9, okay, which is going to be 17. So that's 17 I1, and you're left with minus 6 I2. So that's an equation. Okay, we have formed an equation. That's what equation 1. Leave it like that. Find another loop that you work with. You formulate an equation again from that loop. So which loop are you going to consider? That is in your hands again. It's up to you. Okay, so let's say consider B to C to D back to the point B like this. This is the way that I'm going to take my loop. Okay, so according to loop B, C, D, back to B. It's a closed loop, yes. The EMF we do not have any voltage there, so that's 0 is equal to. Okay, let's move from B to C. Are we maintaining the direction of this arrow, this current? Is it maintaining the way that we took the loop? Yes, it is moving in the same way. So that's 6 times I2. From C to D, are we maintaining? No. C to D, the current is moving this way. Remember, this is how we are taking our loop. C, D, but the current is moving from D to C. It's opposing. As we are moving from C to D, the current is moving from D to C. We are opposing. So in that case, it will be a minus. So that's minus 8 times the current, which is 2 minus I2. Let's consider from D to B. Again, from D to B, the current is opposing. The current is moving from B to D. As we are moving from D to B, we are opposing. The current is opposing the movement, so it's a minus again. So that's minus 6 times the current in this branch. The current in this branch is what? I1 minus I2. So you just have to check, is it maintaining according to the way that you have taken a loop? Is it maintaining or not? If it is maintaining, positive. If not, a negative. That's it. So according to this one that I formulated, this is what I was going to have. Then I can expand the brackets. Minus 8 times 2, that's minus 16. Minus 8 times minus, that's positive 8 I2. Minus 6 times I1. Minus 6 times I2, that's minus minus, that's a positive 6 I2. So you can even transpose the negative 16 to the other side of the equation, becomes a positive. That 16 is equal to, are we having any like terms in terms of current one? So this just I1 here, just this one. So, okay, no problem. So that's minus 6I1. Then considering the part of I2, okay, there are currents I2 there. We're going to consider this is I2. All right, let us just consider I2 here. We also have I2 here. We also have I2 here. So you combine these, what are you going to have at the end? That is going to be 6 plus 8 plus 6, which is a 20. So that's 20 I2. You can even avoid working with negative values, guys. You are the one who is formulating these equations. It's in your hands. You can even avoid working with negative if you want. You can take this to the other side, this to the other side, so that I1 becomes a positive. So it will be 6I1 minus 20I2. I2 was a positive, so it becomes a negative. Then you transpose the 16 to the other side, it becomes a negative 16. This is in your hands. The way that you are going to formulate these equations. So that's we've got equation 2. These two equations are enough for us to obtain current 1 and current 2. So what are you going to do? Solve. Take your simultaneous, take your equations, the first equation. All right, so in this case, we need to solve for I1 and I2. The first equation, taking this side, it was 17 I1 minus 6 I2 is equal to this side, which is 18. Okay, that is our equation 1. Equation 2, from this arrangement that I made, remember I said you can even make it, you can make that subject. Okay, very sorry for that. So as we can see, you have got your current 1 and also your current 2. So your current 2, your equation 2, which is 6I1 minus 20I2 is equal to minus 16. That is our equation 2. So equation 1, equation 2. These are the two equations that we are having. According to the part that I talked about previously, so that we can use our elimination method, we can eliminate I1, we can eliminate I2, depending with what you want, okay? You can even use the substitution method. So I want you to use any method to prove if you are having the same answers. All right, so in this case, let's eliminate current 1. So to eliminate current 1, we're just going to interchange these numbers, the 6 and the 17. You multiply equation 1 by 6. You multiply equation 2 by 17. That is, you just interchange these two numbers that are on the currents, all right? So 6 multiplies everything on equation 1. You multiply everything throughout by 6. Okay, so 6 times 17, that's 102. I1, 6 times this, 6, that's minus 36. We've got a negative there. So it's going to be minus 36 I2, which is equal to 6 times 18. That is 108. Okay, we are done with the 6 multiplying the first equation. You can even name this equation 3, equation 4 if you want. 17 multiplies 6, that's 102. I1 17 and the minus 6 minus 20, that's minus 340. I2 17 and minus 16, that's minus 272. So these two, the part of I1 and I1 from the two equations are the same. So we can eliminate. Are we going to subtract or are we going to add? Guys, these two numbers, they are positive. So 102 minus 102, that's a 0. So you're going to subtract. So you subtract, let's say this is equation 3, this is equation 4. You're going to subtract equation 3 minus equation 4. The way that you present this in your hands, it's up to you. You can just subtract these two equations. So 102 minus 102 cancels. The sign that you have is the one that you maintain throughout. So here we are going to subtract again. So that's minus 36 minus, take note, minus, what are we subtracting? Minus 340. Minus 36 minus 340. So that is going to be 304. So that's 304. I2 is equal to, do the same thing, 108 minus 278. So there's a minus that is controlling the question. So that's 108 minus 272, like this. So minus will be a plus. So this will give us 380 at the end. So you're going to obtain 380. So to determine I1 and to determine this I2, you can just divide by 304. That's it. Just like that. So we've got our current 2. So that was going to be something like 1,25 amps. Just like that. So to determine or to find I1 now, you have to choose any of the two equations, substitute there to determine I1. So I'm just going to take any of these equations. So from, I'm just going to use equation 1. From equation 1, we have got 17 I1 minus 6 I2, which is equal to 18. So substitute what you got in place of I2, we got 1,25. 17 I1 minus 6 times 1,25 is equal to 18. So that's it. You can multiply. If you want, you can just transpose that other side. You can multiply, guys. It's up to you. If you multiply, this will be minus 7,5 is equal to 18. Then transpose the minus 17, minus 7,5 because you're solving. So it will be a positive. 17 I1 is equal to the sum, that is 25,5. So let's divide by 17 by 17, determine I1, and that will be 1,5. It's just like that. You can also use the substitution method. But since you're working with the bigger values now, that is where it becomes a challenge to work with that substitution. But if you understand how to work with those values as they are, it's not a problem at all. So we have got current 1 and current 2 according to the circuit that we are given. So like I said, you formulate these equations according to the loop that you choose, unless you are given a certain situation where they want you to work with a certain loop. They gave you to like working with this loop. On that condition, you'll be limited now to work with the given loop. But if you're not given, it's it's your choice. Unless if you're given that you're supposed to use a certain loop in your calculation. In that situation, you will be limited only to work with what you are given. So answer the question the way that you are given. That is how you answer the questions. The way that you are given there. All right, let us consider this circuit here. We're just gonna have this as our last question. Let's see what we can do. But like I said, even if you check these typical questions, we've actually worked them before from our question papers, this and that. So you can also relate from there. All right, so let's say we are given this as A, B, C. That's we have got D, and we have got E, F, G, and let's say this is H. Given this is let's say this is R1, which is 2 ohms. Okay, let's say this is 2 ohms, and you're also given the current, that is current 2, and you're also given this current as 0.062 amps. So you'll be given these currents and so on. So only that somehow, in some cases, you have to formulate you have to formulate like the currents. If you are not given, in that case, you have to formulate those currents in any other branch that you might be given that is not represented in terms of the current. But if the currents are presented, like in most exam cases, you're going to see that they are going to give you the currents, but not always. That is why we've got a question like this one. So this question, it is the one that can actually help us to understand. Let's say you're given a voltage here of 20 volts and you are given current 1 facing this side. That is, remember, current from the positive. So that is our current 1. Okay. You are being asked to determine current 1 and current 2 again from the same Kirchhoff's laws. How can we determine these currents I1 and I2 from the Kirchhoff's laws? So the first thing is to check, okay, are we having all the currents in each and every branch? If I am to use this loop here, I'm going to see I'll be limited because I do not have a current between H and F. Between point H and point F, there is no current. Between F, E to D, there is no current. From D to C to B, we do not have a current. So the first thing when you are given a circuit like this is to observe properly your currents and start naming each in each branch. In each branch. In each branch that you are given. So, meaning to say, considering these currents, we have to go back to our Kirchhoff's current law. Remember our Kirchhoff's current law. Okay, let's formulate. It's going to depend with which part are you going to start with. Let's consider the branch HF here, this branch HF, where we have got HF between the point H and F. All right. We're just focusing on the currents now. Considering the point HF here, we can see that there is a current flowing towards, which is this current I2. It's flowing towards this junction at H. I2 is flowing to the junction. It's in. I1 is flowing in. I1 is flowing in. I2 is flowing in. So these two, they meet and they flow out to this current, that is current at H, this one. We're going to take it as the current away from the junction. So remember the concept that I talked about, the sum of current flowing towards the junction, which is I1 and I2. They are flowing towards the junction. They must be equal to this one, which is the current. Let's say we call it IX, which is the unknown current. It must be the sum of I1 and I2. They are flowing towards the junction I1 plus I2. So meaning to say in this branch of HF, the current that we are going to use, it's I1 plus I2. This is the current flowing, current 1 plus current 2. Okay. Let's consider from this branch here, from F to E to D. there's a current that must flow in this branch. But what is happening? Remember, we are given the 0,062. This current that we see in this branch, it is the same current flowing from F, G, A, B. It is the same current that we have there. This current. So the direction is like this in this branch here, this 0,062. It was taken like this. It is the same current that we are having there, the 0,062 there. It is the same current that we have here. So let's formulate again using the unknown value. Let's say this is Ix. Remember the current flowing towards the junction, which is towards F. The current that is flowing, the current in, the sum of current in is equal to the sum of current out. Which current is flowing in to the junction? That is I1 plus I2. This is the one flowing in. Which one is flowing out? The 0,062 and this one, the unknown, which is Ix, which is the unknown current. So we want to find an expression of this Ix in terms of these. So we're going to take this to the other side. So it's going to be I1 plus I2 minus 0,062. So this is our Ix. So this unknown current in this branch that we are having from F to E to D, the current flowing there is going to be given as I1 plus I2 minus 0,062. That is the current flowing towards the junction minus this one going away is supposed to give us the remainder, this one. That is how you can find these currents. This is the current flowing at this point at D here. This is the same current that we have from E to D. Remember, FED is the same current there. But from D to F to C to B, there's another current there flowing. And we do not know this current flowing here from D to C to B. Again, let's say this is unknown. The currents flowing towards the junction, towards the point D. Which current is flowing towards the point D? The current flowing in at point D is this I1 plus I2 minus 0,062. This is the current flowing towards. Ix, which is the unknown that we want, and this I1, this one, they are flowing away. So this must be equal to I1 plus Ix. We want to find Ix in terms of take I1 to the other side, I1 and I1 was going to cancel. So it was going to be I2 minus 0,62, which is equal to Ix. This is a known current that we want in this branch. So in this branch, the unknown current that we have formulated is going to be given as I2 minus 0,062. That is your current there. You have formulated the current in terms of the other currents that you're given. So it is not always that you're going to be given all the currents in each circuit, in each branch. So as you can see, each and every branch now, we have got a current. So it's the first thing to locate that. Are your branches having all the currents? If not, formulate. Formulate your currents according to your Kirchhoff's current law. Then after that, now you talk about the voltage law now. Look for the closed loop that you're going to work with. In that closed loop, you form an equation. So in this case, I'm going to take the first loop. This one I'm going to consider. Remember, we want to calculate, sorry for that. We want to calculate I1 and I2. So I'm going to consider this loop here. This loop A, B, like that. All right. So I'm going to consider this loop, the loop of A to B, to F, to H, to F, there to G, like that, up back to the point A. This is the loop that I'm going to take. The way that you take your loop, it's in your hands. So I'm going to consider loop A, B, passing through H, passing through F to G and back to A. Okay. So in this loop, we do not have an EMF. So remember, the EMF is supposed to be equal to the voltage drops, potential drops. So considering AB across this AB, this is the same current from F to G to A to B. It is the same current of 0.062. And it is maintaining, as we can see, it is flowing in the same way that we have taken our loop. So it's current of 0.062 times the resistance. There is a resistance in this branch from F to G to A to B. We only have this resistor of 5 ohms. So current times resistance, that's our voltage drop, our potential drop. From B to H, there is a current and a resistor there. It's a branch there that we have from B to H. Are we moving in the same way that we have taken in terms of the current? The current is also moving from B to H. It's moving in the same direction, so it's a positive. That's 2 times current I2. Current times resistance. From H to F, there's a current, there's a different current there, I1 plus I2. Is it moving in the same direction? Yes, the current is moving from H to F, so it's a positive. So that's the resistance there, which is 1 times the current. Our current is current 1 plus current 2. Current times resistance. From H to F, there's a different current in this branch. As we can see, we are back to F, to G, to this point, we are back to that branch that has got the same current and only a single resistor of 5 ohms. So we formulated an equation, simplify. All right. So that's 0 is equal to the product of these two. That will be 0.31, 0.062 times 5. Then you expand the brackets. That's 2I2 expand by 1. 1 times I1, that's I1. 1 times I2, which is I2. So you can even transpose, take the 0.31 on the other side. That's minus 0.31. So that's minus 0.31 is equal to. So on the left-hand side, we are just having, on the right-hand side, we are just having a single current I1 there. Then we've got I2 and I2 that we can add. So I2, we also have another I2 here. All right. So I1, there's no other part that you're going to consider. You're just going to take this I1 as it is. Then the part of I2, that's a 1 there. So it's going to be 2 plus 1, which is 3. So that's 3I2. So this is what we are having at the end. We have formed an equation. Okay, just leave it like that. That's our equation 1. You move on to another part. It's your way, guys, that you will formulate your equations. Which loop are you going to take? It's in your hands. So in this case, as for me, I'm just gonna consider this loop here from, like I said, guys, it's in your hands. I'm gonna consider from D to H to B. Okay, this one. Okay, it's fine. You can even consider this one if you want, or you can consider this way from D to H like this. You're gonna consider this loop this way. All right, so this is how we're gonna take our loop. So that's from D to H to B to C and back to the point D. So this is the loop that you're gonna take. All right. So in this loop, there is an EMF, there's a voltage there of 20. So you have to consider that. And according to the way that we have taken the loop, it's the positive. This side is maintaining where the positive and where the current is. So it's going to be a positive. It's maintaining. All right. So I want us to consider the voltage drops, which is the PDs from D to H. From D to H, there is a resistor there and there is current 1. D to H, the current is also flowing in the same direction. So there's a potential difference there. So that's current times resistance. So you're going to have 4 times I1. All right. Then from H to B, I want you to take note. From H to B, take note. We are opposing the way the current is taken. The current is moving from B to H. As we are moving from H to B, we are opposing. So it takes a negative. There's a current there too, I2, and the resistance of 2. So that's minus 2 times I2. Okay. Then we move from B to C back to the point D. Is the same current flowing there. But as we are moving from this B and so on, as we are moving, as we can see, we are opposing the direction of the current. The current is moving from D to C to B. As we are moving from B to C to D, we are opposing. So that's a minus. So that's minus 3 times the current that you're given. Remember, in this branch, our current is I2 minus 0.062, just like that. We're done. Expand your brackets, collect like terms. That's where formed an equation. So that's I1 minus 2I2, expand by negative 3. That will be negative 3. I2 negative times negative. That will be a positive. That's 0.186. So take this 0.186 to the other side of the equation. It will be a minus. That's 20 minus this. We are going to obtain 19.814, which is equal to, there is only I1 there. That is 4I1. Considering I2 and I2, that is minus 2, minus 3, that will be minus 5 I2. So that's your formed an equation again. So you've got equation 2. You solve your equations simultaneously, depending with the method that you are going to use later on. So we're going to have our two equations so that we can solve. All right, so remember the first equation, just going to start with our unknown values. That's I1 plus 3I2, which is equal to minus 0.31. Then we take this other side, that is 4I1 minus 5I2, which is equal to 19.814. So these are the two equations that we are given. And with these equations, we can solve with any method. So even if you're to use a substitution, because you can see I1 is easier to work with, you can even use that substitution method. I want you to try that and see what you're going to have. Or you can just opt for that same elimination. Like I said, there's a 1, there's a 4. You interchange 4 multiplies on top, 1 multiplies the second equation. So 4 is multiplying, 4 is actually multiplying everything on the first equation. 4 times 1, that's 4I1. 4 times 3, which is 12I2. Then 12 times this, that's minus 0.31 times 4. You're multiplying by 4. Sorry, I forgot to multiply by 4 there. So you're going to multiply by 4. That will be minus 1.24. Multiplying by 1 does not affect anything. So this will be 4I1 minus 5I2 is equal to 19.814. The two equations can be subtracted since this is positive and is the same. It's a positive 4, positive 4. So you can subtract to eliminate I1. Remember, you want to eliminate current 1. So that's it. As usual, guys, you're just going to subtract them because the positive and positive, the signs are the same. So that's 12 minus 5 also. Minus and minus, that's a plus. So it's 12 plus 5, which will be 17. I2 is equal to, that's minus 1.24 minus this 19.814. So it's minus 1.24 minus 19.814. The sign, the minus, So this was going to give us negative 21,054. All right. Dividing by 17 both sides, dividing by 17 both sides, that is you're obtaining I2, which was going to be minus 1,238 amps. All right, so we are obtaining a negative on this one. It is giving us a negative. We substitute to find I1. Take any equation. You can take your equation 1. You substitute that with a negative as it is. Substitute with a negative as it is. All right, so in this case, I'm just going to take from equation 1. So from equation 1, remember it is I1 plus 3I2, which is equal to minus 0,31. Guys, we can make I1 the subject. I1 is equal to minus 0,31. Transpose this to the other side. It becomes a minus. That's minus 3I2. So thus we can substitute your I2 to determine I1. That's minus 0,31 minus 3 times I2, which is the value that you obtained of minus 1,238. So that's it. So thus we are going to have I1. So if you're to simplify, this was going to be a positive 3,404 amps at the end. So thus we have got our current one. So guys, these are the typical questions that you might be considering. Guys, you can formulate with any loop as long as it's a question that is in your like a conditional way where you it's a choice, like you're making these out of your own, of your like loop that you want. You're making any loop from any loop that you want, any loop of your choice. But in exam condition, they can ask you, they can give you a certain loop to work using this. You do not have an option when you are given like that. You work with that. We could have worked with this loop. You could have worked with the outer part of the, guys, as long you are forming from a closed circuit, that is the idea. So that is it, guys, from Meson African Motifs. Till we meet again.